Now we can go.
Okay, great. So thanks, Willie. I will speak, as you said, about non-existence of graded unital morphisms between Leavitt algebras under Cuntz splices. This is joint work with Willie. And so first, I wanted to make a brief review of the definition of Leavitt algebras, how are they graded algebras, and about their graded K-theory. So let us begin by saying what a Leavitt path algebra is. So throughout the talk, the letter L will be a commutative unital ring. And the Leavitt path algebra of a graph, well, first I should say what I mean by a graph. So a graph is a set E1 of edges, a set E0 of vertices, and source and range functions that determine where does a given edge start and end. And from that, one can construct the associated algebra with generators, vertices, and edges, and then add formal edges, E star, for each original edge in the graph, which we think about as the original edge, but in the opposite direction. And from this associative algebra on generators, one can consider two relations, the Cuntz-Krieger relations, which I will show on screen, but let me just say that this will not be essential for the talk. All that we will use is that Leavitt path algebras are algebras constructed from a graph, and that their K-theory depends on the graph, and we will study their K-theory. So in particular, we'll be interested in two families of Leavitt path algebra, the so-called Leavitt algebras, which give Leavitt path algebras their name. These are the algebras, the Leavitt path algebras of the rows of impedals, which is the graph that has one vertex and n loops. And so Ln is L of Rn. And then the other family that we will care about today is the Cuntz splice of Ln, which comes from the Cuntz splice of Rn, which is this graph here. So we take the original graph, the rows of n petals, and then we add two new vertices and connect them as in the picture. And we will write Ln minus for this algebra. And so the open question about them is that we don't know whether Ln and Ln minus are isomorphic. And this is important for various reasons. But for example, one would like to know in general if this movement, the Cuntz splice, which is adding two vertices and connecting them to a third one in a given graph, is a movement which is invariant by isomorphism of the Leavitt path algebras. And so a specific case of interest is that of Ln. And so in this talk, the idea will be to show that if there are isomorphisms, or more generally morphisms between these algebras, are in a sense ill-behaved. Okay, but to formulate a precise meaning of that, I shall say what the grading of these algebras are. So in general, Leavitt path algebra of a graph is graded over the integers. And the idea is we give a grading on the generators and then check that that is compatible with the relations, the Cuntz-Krieger relations. So we set that the vertices have degree 0, the original edges of the graph have degree 1, and the formally added edges on the opposite direction have degree -1. So one checks this is compatible with the relations on the algebra, and so LE is Z graded. And so in particular, then LE is graded over any cyclic group. Here from now on, except on this slide, I will use Cm for the cyclic group of order m, but for convenience here, if we write Cm as the integers modulo m, then one can give a grading on LE by considering all the homogeneous components of LE as a C-graded algebra and then group them by their remainders in the division by m. So what we're saying is that the homogeneous elements are the same ones as over Z, but now the degree is the original degree modulo m. And so LE for any graph E is graded over any cyclic group. And in particular, one can consider, as one considers the Grothendieck group of the algebra as the group completion of the monoid of finally generated projective modules. One can do the same, but for graded projective finally generated modules. And so there's a notion of CM graded K-theory of LE for any algebra, Leavitt algebra LE. Okay, and an important thing here is that these are abelian groups because they're defined as the group completion of a monoid. But moreover, one has CM action, which is linear on the groups, which is defined by considering a given projective module. And since it is graded over the cyclic group, we can shift the homogeneous components. So say in additive notation, we send the homogeneous component of degree 1 to that of degree 2, the one of degree 2 to that one of degree 3, and so on. And so that gives a CM action on K0, CM graded K0 of LE. Okay, and so the objective for today is to see that there are no unital maps between Ln and Lm minus that preserve any of the CM gradings. So I will say a little bit about partial results that were known already, but the idea is to show that for any M, none of these maps can preserve the gradient. And so in particular, even if their isomorphisms are not, what one could say is that they're ill-behaved with respect to the grading. And so this was known for M equals 2. This is a result of Cortinius of last year. And before that, we knew that there were no isomorphisms between Ln and Ln minus that preserve the Z grading. This is, for example, on a paper of Ara and Parra. Okay, and both of the results are of K-theoretic nature, so the invariants K0, greater K0 appear, and so the idea is to do things of a similar flavor. And for that, we also need to describe the K-theory of LE. And so, as I said before, all that we will use about LE actually is that it is an associative algebra, but its K-theory depends on the graph. And so we can consider invariance on the graph. That will suffice, at least for our purposes. So in general, the graded K-theory of a Leavitt algebra will be computed in terms of the adjacency matrix of the graph. So let me say that first for non-graded K-theory, so for usual K0. So the adjacency matrix of a graph is the matrix indexed by the vertices, which in the V, W entry has the amount of edges that start at P and end at W. And from that data, which essentially is all that we know about the graph, we can see that the K0 of LE is the co-kernel of this matrix here, which is the identity minus the adjacency matrix transpose. Here, well, there are a couple of hypotheses going on. One is that the ring has to satisfy some sort of K-theoretic property. Here I said that L has to be regular supercoherent and K0 has to be Z, but this is satisfied, for example, for a field or for a PID or more generally for an Arnone regular ring. And the other detail here is that in the adjacency matrix, we actually delete rows if they correspond to vertices that emit no edges. So we remove sinks. And so this may be rectangular. And so one should say what the identity matrix means. And what I mean is that is the matrix that at the VW entry has the Kronecker delta on VW. Okay, so that's K0. Now I will speak about graded K0 for any M. All right. Okay, sorry. So from the computation of usual K0 in terms of the adjacency matrix, what we are able to show is that for any M greater or equal to 2, there is an isomorphism between the graded K0 and the co-kernel of the identity matrix minus the adjacency matrix of the graph, but to the mth power. So it's when M equals 1, if you will, then we recover the ungraded K0. And the CM module structure, because these are moreover not only abelian groups, but CM modules, is recovered by multiplication by the m-1 power of the adjacency matrix. And the proof here involves two steps. One is that we know what the ungraded K-theory of LE is, and the other one uses a result of Ada, Hasrat, Lee, and Sims, which says that the graded K-theory of LE can be computed as the non-graded K-theory of a Leavitt path algebra of a sort of M-sheeted covering of E. So here I'm only going to draw a picture, but that is the idea. So for example, if the graph is the rows of 2 petals, like here, and M is 3, then the 3 sheeted covering of R2 is this picture here. We have 3 vertices. So we have like 3 levels. In each level, we put all the vertices of the original graph. And then for each original edge, we add an edge from one level to the next. So in this case, we have 2 loops. So 2 edges from a vertex to itself, which correspond to 2 edges from one level to the other. Okay, and so from this presentation, we can compute the graded K-theory as the co-kernel of the matrix associated to the covering, and then from that, we can reduce to the mth power of AE. Okay, so let me just say one more definition. This is one presentation of the graded K-theory of LE, but we can also give another presentation. We will use both throughout the talk. So this is on terms of the powers of the adjacency matrix. Another way we can describe this is to consider a generator, say tau. Yes.
Question. You need, in order to take a power of A needs to be squared. So you need it to be regular, right?
Yeah, yes, thanks. Yeah, so as I said before, in general, this matrix may be rectangular. That's because we may have sinks in the graph, and so we delete the rows that have zeros. And so in this case, yeah, for that to make sense, one should ask that the graph is regular, so that there are no sinks. So we're deleting no rows, and the matrix is square. Yeah, thanks. Okay, so as I was saying, this gives a presentation of graded K0 of LE in terms of powers of the adjacency matrix. And the other presentation that we will use is to consider tau, generator of the cyclic group. And then we will define the Bowen-Franks Cm-module of a graph at this co-kernel here. So this matrix, the identity minus tau times the adjacency matrix, is a matrix with coefficients on the group ring of Cm, so integers and powers of tau. And this co-kernel, one shows that it coincides with the co-kernel here. So these are actually 2 presentations of the graded K0. In general, one may add coefficients on the ring. Here we are assuming that the ring, the base ring, satisfies the hypothesis that we imposed on the ungraded K0 case. So in this case, we get a graded K0 is exactly the Bowen-Franks Cm-module. Okay, and so as I said before, the strategy is to show that there are no graded maps between Ln and Ln minus by showing that there are no maps between the K0 invariants. And so what we will actually see is that there are no Cm-module maps between the Bowen-Franks Cm-module that send distinguished elements to distinguished elements. So for that, I should say what a distinguished element is. And by that, I mean the class of the free module of rank 1 of LE in this abelian group corresponds to the sum of vertices. Here we think of vertices as basis elements on the domain of this matrix, thought as an endomorphism. And so LE gets mapped to the sum, and a unital map should send this sum to the other, so it should preserve the element 1e. And so we will see that there are no Cm-module maps that send 1 of Rn to 1 of Rn minus, and likewise in the opposite direction. Okay, so I think those are all the definitions. Now I will speak about Bowen-Franks Cm-modules, in particular of Leavitt algebras and their Cuntz splices. So the first case is easy enough. The graph Rn is the rows of n petals, and so it's 1 vertex and n loops. So its adjacency matrix is a 1 by 1 matrix of 1 entry, which has the amount of loops we're considering. And so its Bowen-Franks Cm-module is the co-kernel of this endomorphism here, which gets us the cyclic group of order n to the m minus 1. And we can also check that the distinguished element of the Bowen-Franks Cm-module gets mapped to the element 1. Okay, and well, and also, as I said before, these are Cm-modules, and we care about the Cm action. And so again, one has to check via this isomorphism, what does the action correspond to? And it corresponds to multiplication by n to the m minus 1. Okay, so that's Rn. Now, our second objective is to compute BFM of Rn minus. And so for that, I shall give the formal definition. So I draw a picture, but formally, what we'll use is that its adjacency matrix is this one here. So we have, as before, one vertex with n loops. So that's the n here, which is then connected to a second vertex and back, which has a loop, and it's connected to a third vertex and back, which also has a loop. Okay, so the matrix is this one here, and by definition, the Bowen-Franks Cm-module of that graph is the co-kernel of this matrix. Here we are using the second presentation instead of the first one in terms of powers. And so it's the co-kernel of this other matrix here. Okay, and so what we did here was we considered this, well, first we did computed it for small n, but then what we saw is that one can think of this matrix as the image of this other matrix with coefficients and integer polynomials being projected via the projection from Zx to any group ring of any cyclic group. So we have projection from Z of x to Z of Cm, and that sends this matrix here to any of these other matrices here. And this matrix can be now viewed in the ring Guido of x of polynomials with rational coefficients. And since that one is a principal ideal domain, then we have a Smith normal form. And so up to multiplying by invertible matrices, we can think of this matrix as diagonal. And then what we check is that all those operations can be actually performed in Z of x. So we can do that actually in Z of x. And then by projection, we obtain the same in any group ring of a cyclic group. So by doing that, we can actually replace this matrix by a diagonal one, which has 2 ones, and then this polynomial here. So the Bowen-Franks Cm-module of the Cuntz splice is the group ring Z of Cm divided by this polynomial evaluated at the generator tau. And again, we should check where does the distinguished element go, and one checks that it goes to 1 minus n tau, viewed as an element here. Well, now the action of Cm is explicit because we're viewing a quotient of Cm. Okay, so those are the Bowen-Franks Cm-modules of Leavitt algebras and their Cuntz splices. We shall now see that there are no maps between them that preserve the distinguished elements. Okay, so well, here it essentially says what I just said. So we have these two Cm-modules with a distinguished element, and we will see that there are no pointed maps in one direction nor the other. And one of those we can already do. So proposition, there are no Cm graded maps which are unital and go from Lm minus to Ln. Okay, and so maybe a remark here is that I have been speaking about graded K-theory over finite cyclic groups, and that is because our objective is to show that there are no graded maps over any cyclic group, but if there is a graded map from the infinite cyclic group, then that induces, say, a C2 graded unital map, because a Z graded map is C2 graded in particular. So we can assume here and in all of what follows that M is finite. And so this case amounts to writing that there exists a Cm-module map, which is pointed. So it sends this element 1 minus a tau to 1, and then we do the computation, use Cm linearity, and that gives that 1 equals 0. So it's a contradiction. So that's essentially it. If it sends 1 minus n tau to 1, then using linearity, we get that this is actually 1 minus n tau times the image of 1, but 1 minus n tau in the cyclic group is 1 minus n to the m, which is the order of the group. So this thing is 0, and it should have been 1. So that proves one of the directions of our result. Okay. So the other part requires some lemmas, and it is that there are no maps on the other direction. Okay. One thing that we will need, and we can state for many other graphs, so we need some hypotheses, but we can state in general, is a criterion for the order of the Bowen-Franks modules, as the Abelian group says, we need a bound on the size, which we will use, but I will state in general. So if E is a finite regular graph, so as we noted before, we need to ask that the graph is regular for everything to make sense, because we need to remove the sinks, then we may say the following. If the characteristic polynomial of the adjacency matrix of the graph has no complex roots, so all the roots are real, and the C2 Bowen-Franks module is finite and non-trivial, then actually all of the Cm Bowen-Franks modules are finite, non-trivial, and bounded below by the order of the C2 one. Okay. And the sketch of the proof is, once again, we will use the Smith normal form in a way. So if we use the presentation of the Bowen-Franks Cm module as the co-kernel of this matrix here, then we know that as an abelian group, its invariant factors, the product of them, is equal to the determinant of the matrix, which again, one can state as evaluating the characteristic polynomial of this other matrix at 1. And so what we know is that if this determinant is 0, then some invariant factor must be 0. So the group is infinite, but otherwise we know it's finite. And moreover, we know that the order is exactly this determinant here. And so if say BF2 is finite, then this value with m equals 2 cannot be 0. And so the roots of this polynomial cannot be 1. But one knows that powers of a matrix and characteristic polynomials are related in a concrete way. So the roots of the characteristic polynomial of a power of A of E are m powers of the roots of the original characteristic polynomial. So if in the case m equals 2, none of those are 1, and none of the roots are complex, then we know that for any m, this will never be 0. So that shows that any of the Bowen-Franks modules are finite. And the bound is proved likewise. One expresses this explicitly as the product of 1 minus all the powers of the roots, and then uses the triangle inequality to bound out below by the case m equal to. So that shows that if BF2 is finite and non-trivial, then all of the others are finite and non-trivial, and their order is at least the one of BF2. Okay, and we will use this only in the particular case of the Cuntz splice of Rn, which satisfies this hypothesis. And what we will use is that these are rounded below by this quantity here, so 3n squared minus 2n minus 1. In particular, these are all non-trivial. Okay. So now we will need 2 more technical lemmas, and that will essentially show the main result. The first one, maybe as I've written it, it's not quite explicit, but we will show that if there is a graded unital map from Ln to Ln minus, then this polynomial belongs to this ideal, and this ideal is relevant because it gives a different presentation of the Bowen-Franks Cm-modules. So explicitly, we know that the Bowen-Franks Cm-module of the splice is the group ring of Cm divided by this polynomial psi evaluated at the generator. So that is the same as considering first the integer polynomials, then divided by xm minus 1, and then dividing by psi of x. So this module here is the same as the Bowen-Franks Cm-module of Rn minus. And so that's why we're interested in knowing whether this element is in this ideal or not. And again, this kind of result is just assuming there is a map and checking where the distinguished elements go. So if there is such a Cm graded unital map from Ln to Ln minus, then there is a map between this between the Bowen-Franks Cm-modules, which are the cyclic group for the Nm minus 1 and these other quotients here. And mapping 1 to 1 minus nx forces us to have that the class of 1 minus nx is, well, equivalently 1 minus nx times 1 minus n tau, because the action of tau here is that one of x. And they then by hypothesis, this element here is the image of the distinguished element of this group, which was 1. And once again, by the Cm linearity, we can write 1 minus n tau inside the parentheses, and that is 1 minus n to the m, which is the order of the group up to a sign, of course. So at the end of the day, that shows that this class here must be 0, and so the element itself must belong to the ideal. Okay, so that's a technical lemma, and its usage is that if there is a map, then we have this result, and if we have this result, then actually the ideal can be presented in a much more concrete way. So again, for any n and m greater or equal than 2, we will define, we will give a name to the ideal we were considering, and we will assume this element belongs there, which is, of course, satisfied if there is a unital map between the Leavitt algebras and the Cuntz splice. And in that case, the ideal I of nm has this presentation. Okay, and this is again a technical result, but I do want to stress some parts of the proof, which I do in many calculations, but especially the first step. So what we see first is that in this ideal, assuming that 1 minus nx is there, then n minus 1 squared is an element there too. And to show this, well, we first computed the cases for small n, and what we realized was that there were always polynomials of fixed degree, Pn and Qn, that exhibited n minus 1 squared as a combination of 1 minus x squared, which we assume is in the ideal, and this other polynomial psi, which by definition is in the ideal. So that's for small n. But then, so what we thought it might be happening is that these polynomials had coefficients which were polynomials on n. And so if they are effectively polynomials on n, then we can compute them for small numbers of n and hope that the polynomials considered have relatively low degree. And so if we polynomially interpolate, we consider the Lagrange interpolators, then that should coincide with the actual coefficients of P and Q. And so that's what we did. And once we had those candidates of coefficients for P and Q, one can check that directly by doing the computation. And so that shows that in general, there is a combination between xi and 1 minus x squared, which gives n minus 1 squared. Okay, that's the first step of the proof. And I wanted to stress that because this shows already that there are no maps between L2 and L2 minus. So if we stop here, at least we got the case for n equals 2. And that is because we said before that all the Bowen-Franks Cm-modules of the Cuntz splices are all non-trivial. We in fact have a lower bound on the order the modules. In particular, that holds for 2, but we're saying that 2 minus 1 is in this ideal. So this ideal is actually the whole ring, and so all the quotients are trivial. So that contradicts that we had said that these are all these quotients are non-trivial, and we had a bound of the order. Okay, so the first step shows that for n equals 2, we have no maps. Then the step 2, the strategy is similar, and what matters is that in the same fashion, one can show that 1 minus nx, so there are no squares here yet, is the same as x minus 1 modulo this ideal. But now, if we assume that this one squared is 0 modulo this ideal, then the same should happen for x minus 1. So what we get is that x minus 1 squared is in the ideal. And that already shows the result, because if x minus 1 squared is in the ideal, then we might add it as a generator for free, and then we reduce the other 2 generators by x minus 1 squared, and that's what gives the presentation here. Okay, and with that, we are ready to state the result. So there are no CM grade unital maps from Ln to Ln minus. Then the first lemma shows that 1 minus x squared is in this ideal. Now, the second lemma shows that under these hypotheses, we have a concrete presentation for the ideal that defines the Bowen-Franks Cm-module. And so the Bowen-Franks Cm-module of R minus are these quotients here. And now we use 2 facts. One is, as I said before, M is finite here because we can assume so, but moreover, CM graded map is also CD graded for any divisor G of n. That's a general result. If one has a G graded map, then the same map is graded for every quotient of G. And so we can contradict that there are CM graded maps for M prime, and that will imply the result for any M. So once we have that presentation and we assume that M is prime, then with techniques as in the lemma before, one can actually check that this ideal is way too large in a sense, and so the quotient is too small. Specifically, we show that these quotients are cyclic groups of order less than the bound that we had found. And so that contradicts the first non-triviality criterion that we had shown. And so that's the spirit of the proof. And that's all I wanted to tell.
Okay, so thank you, Guido. Are there any questions from the audience? I hope they're still there. Well, I have a ridiculous question, which is, you said that I had proved this for M equal 2 and any n. I wasn't sure if, I don't quite remember if I dealt with any n or just M and n.
It might be M equal 2. Yeah, that might be the case. Yes. Yeah, now that I think about it, it was certainly 2 graded because the grading actually came from the involution on the algebras. But yeah, I think so. Because if I recall correctly, the calculation is about 2 specific groups. One is Z3 and the other one is Z7.
Yeah.
There were no family of groups, I mean, so yeah, most likely n equal M equal 2.
So just one question.
Yeah.
So this proof is elementary. So you don't use any K theory or any things like this, right?
Yeah, this is totally elementary. Actually, what we use about K theory is that we can compute it in terms of the JCC matrix, and we use the result about coverings of the graph. So once we can state it in terms of powers of the matrix, then yes, this is a Smith normal form and checking that some ideal has a specific presentation. Yes, indeed.
I mean, it is K-theoretic in the sense that two K-theory groups appear, but
No, otherwise it's elementary. Okay.
yeah.
Yes.
Yes.
Okay, thank you.
Welcome. Okay, so if there are no further questions, I will stop the recording.